Okay, we've just seen that the function, the derivative of a function, is given by the formula limit h as h goes to 0 of any point x plus h minus the function at any point x. Here's some terminology. If the derivative exists, we get some situations where it doesn't exist, we say that the function is differentiable. So if the f prime exists, then the function f is differentiable at whatever x you use. Just say that f is differentiable. Because what we're going to see a lot of times in our definitions and our theorems, remember in the chapter 2, whenever we did a theorem or a definition, it always says that f is a continuous function. Let's see how that connects to this stuff, because think about it. If it's continuous, that means it has to be a function. Does that mean that the derivative exists in all points on that continuous function? Where would be the only place that the derivative doesn't exist right now? What would you think?
It's 0.
What if you had a horizontal line? The only place you can see that the function does not have a derivative, which means the derivative is the slope, where does the function not have a slope? Vertical lines. It's not a function. The function is undefined because the slope is undefined. So that's one example. And since it's a limit going to a point, it has to approach from both sides. So with that, where have limits not existed? Well, we have discontinuities, we have holes, we have points. But yeah, we'll get to those definitions in a little bit. But now we're saying if a function is differentiable, then we can start thinking about it. That means that f of x has to be continuous if it's differentiable, because it has to, all the derivatives have to exist on that domain. Where's my first example? So let's look at calculating derivatives from the definition. There are different ways of writing the term derivative. If f of x is a function and the derivative exists, we know that we could say this. We can also say this, that d means it's differentiable. The differentiable function f with respect to the variable x. So our first example we did was 1 over x. What was the derivative of that function? Very good. -1 over x squared. So what we can say, using this terminology, we can say it was the derivative of 1 over x with respect to x was -1 over x squared. And there are a whole slew of those symbols we use. Example 1. Differentiate. Well, again, when we hear the word differentiate, what does that mean? What does differentiable mean? Differentiable means we could take a derivative of it. Because this is the derivative. So if I say differentiate, that means I'm saying find the derivative. So what we're looking for is find f prime of x. So differentiate this function. We're looking at from the definition. To find the derivative, what formula do I use? So to find f prime, I got to use the limit as h approaches 0 of f of x plus h minus f of x all over h. I have f of x, so I have to find f of x plus h. Which is x plus h over x plus h minus 1. Now I can plug those in there. The limit as h approaches 0 of f of x plus h, which is x plus h minus 1 minus x minus 1 all over h. So what do I need? What I have to do algebraically now, because calculus is done. Now it's the algebra. What do I have to do to solve this one? I have to get a common denominator because I need to add these two fractions together. So that means this one needs an x minus 1 over x minus 1. This one needs an x plus h minus 1 over x plus h minus 1. So the limit as x approaches zero, or h approaches zero. I know I'm gonna have a common denominator on the bottom. So the top is gonna be x minus 1 times x plus h minus x plus h minus 1 all over h. Okay, good. Limit as h approaches 0. So on the bottom, we have x minus 1, x plus h minus 1. So on top, we get x squared plus xh minus x minus h minus x squared minus xh plus x. Because remember, rules of algebra, rules of thumb of algebra, everything after the minus sign, after this minus sign, which is here, all this stuff has to cancel. Limit as h approaches 0. The x squares cancel. The negative hx cancel. And the x's canceled. So we have x minus 1, x plus h minus 1, and a negative h on top. This is an h over 1 on the bottom. Leave the top fraction alone. Flip the bottom. Cancel. We have negative 1 over x minus 1, x plus h minus 1. Take a minute. Now we can take h goes to 0. So that one disappears. So we have negative 1, x minus 1, x minus 1, which makes it negative 1, x minus 1 squared. Pretty similar to the one we had earlier. Let's look at example 2. If I'm going too fast or if I turn a page too quick, make sure you tell me. I won't go back. I just want you to tell me now. Two things. A, find the derivative of f of x equals square root of x for all x is greater than 0. and it'd be find the tangent line to the curve y equals radical x at x equals 4. Apparently, this means equation of the tangent line, the EOL. All right. So A, it says, I want the derivative. So f prime of x is equal to the limit as h approaches 0. F of x plus h minus f of x. Okay, now since we have a radical here, the square root of x plus h minus square root of x. I'll show you, we can do it that way. Yeah, let's just do it both ways. I'll show you the other way. So if we have the limit as h approaches 0, we have absolute value of x plus h minus the absolute value of x over h. If we plug in 0 for h, what would we get in our equation? Zero over zero. Because it'd be radical x minus radical x is 0 over 0, which is a good sign. How do we go about fixing that or solving it? Well, we'll see if we could, can we factor anything? No. Can we multiply by anything to make it work? Since we're dealing with radicals, if we multiply both the top and bottom by the conjugate of the numerator, that'll help fix our problem. Yeah, so if you ever have radicals, usually the conjugate is usually the thing, because what happens when you multiply the conjugate to a radical? It just makes the radical disappear. Or it goes the same thing with imaginary numbers. On the bottom, it's h times radical x plus h times radical x in parentheses. So what do you think we got to do on top? FOIL. This times this gives us square root of x plus h squared plus radical x plus h minus radical x plus h minus radical x squared. The middle terms cancel. we have radical x plus h squared, which just gives us x plus h, minus radical x squared, is just my x over h, radical x plus h, plus radical x. On the top, the x's cancel, so we just have h on top. The h is canceled. So we have a 1 on top. Radical x plus h plus radical x. We can't do anything algebraically anymore, so we take h at 0. So we get 1 over radical x plus radical x equals 1 over 2 radical x. Okay, that's the first part. Any questions about that? You have to find the f of x plus h, then since we're doing with radicals, do the conjugates. So we know that the derivative of the function is, this is f prime. Now, question B is asking us find the, no, it just finds, find the equation of the line to the curve at x equals 4. B. Find the equation of the line to the curve at x equals 4. And we just found the first derivative was 1 over 2 radical x. So what do we need to find the equation of a line? To find the equation of a line, we need a point and we need a slope. Do we have either of those? No. At least not yet. A point is an x and y component. It's an ordered pair. We know what x is going to be. If we take this and plug it in place here, we can find the y. To find the point xy, so it's a square root of 4, which is 2. So the point we're dealing with is 4, 2. So that's what we're going to use for the point. To find the slope, the slope is equal to the first derivative, which is 1 over 2 radical x at x equals 4. So the slope is 1 over 2 radical 4 is 1/4. This is our slope. To find the equation of a line, we need to find y equals mx plus b. We have m, we have m, we have y, we have m, we have x. The only thing we don't have is b. This is x, and that's y. So 2 equals 1/4 times 4 plus b. The 4's cancel, so we have 2 equals 1 plus b. Subtract 1. B equals 1. M equals 1/4. Plug those into your equation. And there's our equation of the line tangent to the curve at that one point. Right, so see, the calculus was only the first step. Everything else we just did in those last 3 or 4 sheets were all algebra. So let's see what we've done so far. So the derivative of 1/x gave us what? -1/x². The derivative of the square root of x. So these we can keep on using as quick reference instead of going through the whole process anymore. If you ever see a 1/x type of equation, then just make that derivative as -1/x². Notation of a derivative. So for any given function, f of x, the derivative can be represented in each of these ways. And the derivative of f of x. These are the general forms. And if you're looking for the derivative at a certain point, then you could find these by putting down that value. Are we always restricted to give derivatives of only one variable? In other words, can I only do the derivative of X? There's no. Because what we're gonna get to, we're gonna look at equations where you have multiple variables inside an inside a function. When that happens, we'll look at functions like this, where we're gonna have the derivative of X, Y, and Z of some function. What this says is the function with variables X, Y, and Z. But in this one, it says find the derivative in this particular order. Find the derivative of the function with respect to X, then with respect to Y, and then then the Z. Depending on how those are arranged, it'll come out a different function. Graphing a derivative. They're not going to be the same graphs. What I'm saying here is this. Look at this example. In this first graph, we have our function. This, as you said, it's defined as our function f of x. Each of these dots are certain points. They each have their own slope. Remember, the slope is the first derivative. So for each of these locations, this is f of x. This graph is the function f prime of x. This is the derivative, the graph of this derivative. So in this first point, what is the slope of that graph? That graph is 0. So at this value x, whatever that is, the a prime is going to be on the x-axis because the slope is 0. When the slope at b goes to -1, it drops down to because the slope is, this is the y prime part. The slope of this one is -4/3, which is -1/3. It will go on further. That's 0. It goes back to 0. So you see that this graph is above the x-axis, but the function graph with respect to the derivative, if it's a 0 slope, it's on the x-axis. Here's a 0 slope, it's back on the x-axis. Then above it, it's above. Below, it's below. So what this graph tells me is this. If I look at this graph right here, it's telling me that at whatever value this one is, it's a flat line. It's a horizontal line. Then from there, it goes down. So eventually, this one is at a 1-to-1 slope, -1. Then at C, it starts tapering off. At D, it's a horizontal line again. And then it starts going back up. You have to be able to look at the graph, make the function, the derivative graph, and then go backwards. Look at the derivative graph and tell me what the graph looks like. So let me see if there's an example of that. No, it's not. Well, I'll look for one and we'll talk about it next time. So let's move on. Differentiable functions on an interval. One-sided derivatives. So I could take derivatives at specific side directions if I go for the left side or for the right side. This is come from which side? So this is a left-sided derivative. And conversely, I could do it at the other direction. That's the right side. Now, give me an example. When would that matter when you're taking one-sided? What's that? What kind? Continuous? I mean, no. Continuous functions is always, give me an example of a function or what would happen to a function that you only looked at one side of it? Which we've done examples like this already. Have you ever seen, when have we ever taken the limits specifically on one side? We're not talking about continuity just yet. So when would you need to take a derivative or the limit from one side? Does that example remind you anything? Yeah, we're going from -2 to 2. We're looking, when we find the derivative, we're looking for the slope of the function. So the slope is horizontal there. And what's happening at 2 or -2? What's the slope at -2? I know what you meant, but no, not until you get it right. What does it look like? What is the line gonna look like at -2? the tangent line. Oh, put your pen there. This is your slope line. As it goes to 2, what happens? It's vertical. So what is the slope of a vertical line? Undefined. So as we go to an endpoint of an interval, the clue was here, differentiable on an interval. I can't take a derivative at -3 because it's not on the interval. Since this is the equation of a circle, I know that at 2 and -2, we have vertical lines, undefined slopes. So that's why I could take a derivative from one side, and I could tell you as the slope gets closer to it, it's going to get more and more and more and more vertical. Let's look at example 4. Already there. Show that the function y equals absolute value of x is differentiable on -infinity to 0 and 0 to infinity, but not at x equals 0. So how's this gonna work out for us? What is the function absolute value of x? What's the graph look like? It's a V. Our first domain is from -infinity to 0. So since it's the absolute value of x, I think of it in terms of this. The y-intercept is the origin, so that's gone. What is the slope of this side? What number is in front of x? 1. So on the left-hand side, if x is negative, what value is in front of x? The slope, if x is less than 0, the slope is -1. When x is 1, y is 1, and so on and so forth. If x is greater than 0, the slope is +1. Now, do you see why it doesn't exist at 0? Because as we're getting closer and closer and closer to 0, on the left-hand side, it's -1, -1, -1. On the right-hand side, it's +1, +1, +1. So they're not going to the same side. They're not approaching the same value. So let's look at this. Let's prove this mathematically now. Let's look at x equals 0. So we're looking for the derivative as limit as h approaches 0 from the left, which would be f of x plus h minus f of x. The limit as h approaches 0 from the left. X is 0, so I have 0 plus h minus 0. But remember, the function was absolute value of x. The limit as h approaches 0 from the left. H, so this is h minus 0, that's gone. So as h approaches 0 from the left, where does this go? All my h values have what sign? Negative, because I'm going from the left. So this makes it positive. Positive divided by negative is -1. So now the other side, if I'm approaching 0 from the right, it's going to be 0 plus h minus 0. It's going to happen the same way. We're going to have absolute value of h over h. They're both positive values, so it's going to be a positive one. Since the two directions don't meet the same thing, the limit doesn't exist. Last one. Example 5. The function's f of x equals square root of x. And originally, we said that x had to be greater than 0. What's our derivative? Very good. So it's true for as long as x. What happens if x equals 0? Ooh, we might. No. If x equals 0, what happens? Well, we got to look at the limit as h approaches 0 from the where? Yeah, because it's and what goes here in the function? 1 over 2 x plus h minus 1 over 2 x. Oh, I'm sorry. That's the derivative. We use this function. X plus h minus x over h. Now we're saying that our X value is 0. So it's limit as H goes to 0 from the right of 0 plus H minus 0. The limit as H goes to 0 from the right, absolute value of X or H minus 0, which is gone. So as absolute value of H over H, as H goes to 0, what happens to that function? We can tell that by looking at, I mean, we're looking for the horizontal asymptote, or the vertical asymptote. What is the exponents of the denominator? What is the power of the denominator? 1. What's the power of the numerator? 1/2 square root. Since the denominator has a larger exponent, as we're going to 0, what happens to this function? Goes to infinity because the bottom goes to 0 faster. Think about it. If we had a square root of X over X, what that would be equal to is 1 over square root of X. Because doesn't square root of X times square root of X equal X? Doesn't this equal that? So these cancel, leaving 1 over. As X goes to 0, we have 1 over 0, which is infinity. So that's how come in our original function, it says X has to be greater than 0, because at 0, it goes to infinity. Now, why is that? Let's look at the graph. As we get closer and closer and closer to 0, where's the graph going? Where's the slope of that graph going? Eventually, it's going vertical. So that's why we can't take a derivative at the beginning point. Okay. Actually, it's pretty much it for that whole section. The only thing last part is the derivatives of functions are continuous. We talked about it earlier. If a function has a derivative, that means it has to be continuous because it has to exist at that point. Okie doke. That's it for that. We're done with the first 2 sections. So have a great, safe weekend.